So where do we leave off? We talked about, so last time, we talked about Mcmullen's conjecture, which is, as I said, it's a kind of vertical problem. So fix your favorite real quadratic field and fix some alphabet, finite alphabet, with Hausdorff dimension of the limit set of this alphabet being bigger than a half. Then he guesses that the set of A0, AL periodized in K with all of the AJ in A, this set grows exponentially with L. Okay, so I want to explain the ELMV problem. But to do that, let's recall some more stuff. So we talked about, let's see, I'm trying to remember what we talked about. We talked about that the upper half plane has a tangent space and a unit tangent bundle. So we have points and vectors. And we talked about how this is isomorphic to G itself, G being SL2R, PSL2R.
We talked about geodesics.
We talked about geodesics. Now, do we talk about closed geodesics? I don't believe we talked about that. Okay, so we talked about the geodesic flow. So phi t, the time t geodesic flow that takes a point in the unit tangent bundle and flows along the geodesic determined by that point meaning point and vector, and moves a distance t. So this hyperbolic distance is t, and this is, if this is z zeta, z being the base point, zeta being the direction, then this is phi t of z zeta. So this is the geodesic flow. Geodesic flow.
About the Mcmullen conjecture, I guess. When you and Bourdain have found this, like, for these ideas that you could use a similar approach, did that reignite interest in the problem?
I suppose so. Unfortunately, it didn't reignite all that much progress. It's just a hard problem. Yeah, no, actually, that's not true. There were a couple of, there was a paper by someone whose name is escaping me now, a French mathematician who did his PhD on relating Zaremba's conjecture to Mcmullen's conjecture by finding a very clever way of knowing something about the finite continued fraction and playing a game on these partial quotients to create a periodic continued fraction with some control. So I can't come up with his name right now. There's been some progress, but nothing that I'll report on at this moment.
Nothing on the level has been done in the,
as in some of the others.
The Zaremba conjecture itself.
Yeah.
Okay.
So there's a corresponding flow. The corresponding picture on G is right multiplication, the corresponding to the geodesic flow under this identification. I think we did talk about the Gelfand and Famine. Gelfand, of course, was here for most of his later years. Famine observed that there's this is a geometric and dynamical setup, and there's a corresponding algebraic setup that the geodesic flow corresponds to right multiplication right under this identification. Of course, what's the identification? It's that G in G gets mapped to GZ, exactly, GI, G up, where G acting on Z and zeta is the usual fractional linear transformation in the Z direction. And exactly what we worked this out, I think, that it's zeta over CZ plus D, C. No, I can't. That doesn't help because this thing's in the way. Oh, that's fine. How am I going to do this? Okay, let's go like this. But I can do this. Technology. Give myself room. Okay. So it's fractional linear transformation in the z variable. In the zeta, it's zeta over cz plus d, not norm squared, but just squared as a complex number. Okay, so that was the action. That was this identification. Under this identification, the geodesic flow, the time t geodesic flow, corresponds to right multiplication by the diagonal e to the t over 2, e to the minus t over 2. Okay, so this is a sub t.
Right.
All right. So now let's think about the upper half plane modulo gamma. Let's say gamma is SL2Z.
You proved that this was you proved what the fundamental domain was.
Right. We saw the fundamental domain. And my claim is that so this is some manifold. Let's call it, I don't know, M. No, I'm going to use M for matrix later. Let's call it Y. This is some manifold, and we can consider, again, the unit tangent bundle to this manifold, which I'll call X. Okay, so as before, we have not just points, but points and tangent vectors, and we can identify two things if they differ by SL2Z on the left. Okay, now I have to fix this. Like that and like that. And then I can move it all the way over. Okay, perfect. So the geodesic flow acts on the right, whereas gamma acts on the left. And so the geodesic flow, in the same way, phi t acts on the unit tangent bundle of the modular surface. And so you can flow at time t, except what happens is, so there's two ways that I like to think about this. One way is that you have a point in the fundamental domain with some tangent vector, and then you flow, and when you try to leave the fundamental domain, you just go to the corresponding place in the next fundamental domain. In other words, you move yourself back into the fundamental domain and continue flowing after that.
T inverse or S.
Exactly. Those are the bounding points, with the T being translation by 1, S being inversion through the unit circle. This is all familiar, right? Okay, so that's one point of view. Another point of view, so viewpoint 1 is always resetting back into the fundamental domain, flowing and resetting back.
The other ways, like you have the equivalence classes.
Exactly. Viewpoint 2 is really what H mod gamma means, is that every G in, I want to study not G. So by the same token, we have an identification between the unit tangent bundle of the modular surface with just the quotient G mod gamma instead of H mod gamma. Since G is the unit tangent bundle of H, G mod gamma is the unit tangent bundle of H mod gamma. Is identified with this unit tangent bundle in exactly the same way. So if we have a G, we can think about G in the quotient, or we can think about the coset gamma G. Is the same thing as saying the space of cosets. So what does that mean? That means if I have a single G, wherever it is, it's really the full orbit under gamma of that G and all the different directions that it might point, depending on how it gets moved to.
You have some nice pictures on this. Right?
Well, that's what I had coded
go.
up there. Okay, so this is some point Z and unit tangent vector zeta, which you can think of as flowing in as a broken ray, or you can think of the full coset. And when you flow by time t, so this geodesic flow, time t geodesic flow acting on these, is that all of them flow at the same time. They all start moving. And actually,
the coset definition.
Right. And so what this is that there's one window in which you're following this flow, but really the flow is happening everywhere.
Being represented as just from the fundamental domain.
Yeah.
Exactly. So when you see this, what's really going on is you're flowing everywhere from the full set of representatives, and just in the fundamental domain is where you see this line. Okay, does that make sense? Well, so sometimes, so what does it mean to be a closed geodesic? When does,
Before you change
Please.
topic, in the first, the Pacman like case, the first one.
yes,
I think when we were thinking about this, we didn't have a very good idea for the S. So for the translation, it's clear what's happening, just move the vector. But for the other one, for the one below, it was a little bit unclear. I don't think we arrived at the very satisfactory answer. So if you go like this,
yes,
can you guess how it will go up?
yes.
So the thing is, what we found out was the angle.
The
Right, the
angle.
second coordinate was like changes in a kind of strange way.
Yeah. It was something.
So I'm trying to go like this, right? I'm trying to continue like this, but this half is identified with this half.
Okay.
And so that point comes over here,
Right.
Yeah,
With what
that was
direction?
fine, but not the vector.
and the vector should go in the symmetric, should go like that. Should come like backward from where it came, so that this angle is the same as that angle. This is because of the cone point.
So it's like.
Let me try to draw a better
We
picture.
weren't able to work out the details.
I think this was worse, or maybe it was just blind. I mean, of course, that's also.
Yeah, maybe it was obvious and we didn't see it, but like, we did try to like, we took the action, right? And
Yes.
then, like,
You apply S
Yes,
to how it would go to the unit.
right, to a pair of coordinates, and then we tried, right, the location that it's symmetric, that was very clear. The direction part, yeah, I think we.
yeah, so it should come out on the same angle as it came in. Let's see if I'm right about that. So it comes in on this angle and it comes out on that angle.
It definitely looks like that, but,
Oh, how do you work this out?
yeah, how do you work it out?
Oh.
That's what we were wondering.
It's not hard. It's a little calculation. Should I make it an exercise? You're telling me you want help with the exercise. I mean, it just comes straight from this.
Right, so we tried to literally do that. But
Yeah.
then, like, when we.
So, okay, so if you're coming in at a point, all right, I'll do the exercise with you. So what does this really mean? Z is a point on the unit circle. So here's your Z.
Right.
And zeta, what's zeta? Zeta is some constant. I don't know what depending on what the height of Z. I mean, the constant is the imaginary part of Z. And then e to the 2 pi I, let's see, we're measuring theta from the vertical. Okay, so let's say this distance is I guess negative theta. So e to the I theta. Okay, so Z is on the unit circle. There's this is probably the imaginary part of Z or 1 over the imaginary part of Z, something like this.
What is theta in your picture? In your picture, you have minus theta plus pi over 2.
So I'm going from I up. I up is angles is what I'm considering angle 0.
Okay. So that angle is literally theta.
So that this angle is literally theta.
Okay.
If you want to think about it this way, zeta is centered here.
Yeah.
Okay. So then now I apply this formula.
Second action.
So this is C is 1, D is 0, the element gamma, the element S in gamma.
The second derivative.
Right. So all I get is zeta over Z squared.
Okay.
Okay. So I get S of Z gamma is it sends Z to -1 over Z, and it sends zeta to zeta over Z squared. Because this is CZ plus D, S is
Right.
0,
Minus
-1.
over Z,
Yeah.
and then you square it.
Yeah.
Okay. So this we already worked out. This is going to go
Right.
over here. And now what is this? Well, it's on the unit circle. So this isn't going to change the absolute value. So the zeta is still going to be, I mean, that's just the fact that that this action does take you from the unit tangent bundle to the unit tangent bundle.
But then like that squared there is gonna change your angle like by twice, right? That's like.
By twice the location of, yeah, so wherever the zeta was, it gets spun around by twice the distance from here. Twice this angle. So see, the difficulty is, I think, that the angle, one angle is an angle off the vertical. And Z, you can think of as Z being the angle in polar coordinates, which is an angle from here.
I don't understand why we count Z differently. Like, shouldn't we just count it as a complex number? And if we do, shouldn't we, I mean, why is the theta not?
Well,
Why can you count it from the vertical? That's my question.
it depends on which, what zeta means. So zeta to me is a vector off of I up, because I took G and I acted on it by I up.
Yeah.
So I want the identity. If G is the identity, I want this to be I. Well, okay, so let's call it I. Fine. Let's change this. Let's change this to I comma I. So it's really a complex number.
Maybe yours is better because we failed. So maybe your consideration is probably better. I don't know.
Anyhow, if let's see where this takes us.
Yeah, let's, so I'm going to change this to, well, it's just zeta. Zeta is now a complex number. Okay. And so what happens when you replace zeta, which was some complex number, with some, so it's some angle, and the absolute value of zeta is related to the imaginary part of Z, right? To make it a unit vector with respect to the Riemannian structure. Okay. So, so when you divide by Z squared, this is going to be some simple computation about this. This is going to be like a little bit of Euclidean, symmetry and so on. And the fact that this is a unit circle and there's going to be some similar triangles like this. I think you guys can do this exercise.
Okay. We'll retry.
Yeah, because what is Z squared? Z is this vector. So Z squared is that, and 1 over that's over here. Right? Z is rotation by whatever the angle of Z is. And it's in this range from whatever this is, 60 degrees to 120 degrees or something. So 1 over that squared.
Okay, what you're saying is true for that root of unity kind of thing, but like if you're different, then you might not end up like literally like lined up right behind. Right? Like in the case where you said, right, like 60 and 120 degrees, then that definitely has to work. But
that's the only place where this transformation would be applied.
But the angle of Z could be different, right?
The angle of Z? Z
Yeah.
is along this ray. That's the only time that we're applying S.
Yeah, along that ray, yeah. But its angle within that ray.
Is anything
different.
between 60 and 120.
Yeah.
Okay. So then you do some, the fact that the circle is orthogonal to the radius, and you follow this angle around. And what should happen is that this angle, so what do we want? Yeah, let's not do this right now, but whatever this angle was, it should be, whatever this angle came in as, it should be the angle that this one comes out as in the other direction. I think that's right. So here's a funny thing that can happen. And actually this will be relevant. What happens if something comes right into, let's see if this, this is one thing I do know for sure. If you get something that comes right into this central point, what happens to this ray? Does it come out this way? Yeah, so this is,
that's a fixed point under.
yes.
So it stays like stuck.
Well, Z is I. Z is I. So what's 1 over I squared? -1. So you get minus zeta. So immediately after you apply this transformation, zeta is pointing exactly back the way it came. So if you hit this point, this orbifold point, the way you bounce off the orbifold point is to come right back from where you were. It just, wherever you're coming to me, I turn you around, go back from where you came. Okay, so that's a hint as to your intuition. Now move off of that a little bit. Yeah, so maybe it's saying it should go that way. No. the dynamics, okay. The billiard in SL2Z is the geodesic flow in SL2Z is the double cover of the billiard on inversion through these three. So billiard means you bounce off the walls instead of going through to the next wall, you reflect across this wall. So this is the 2-3 infinity triangle group. You know what I mean by that? Hecka 2-3 infinity triangle group. So 2 means there's a pi over 2 angle, 3 means there's a pi over 3 angle, and infinity means there's a pi over infinity, in other words, 0. These two are parallel. So this is the reflective 2-3 infinity triangle group. In other words, it's symmetric. There's a mirror. Each of these walls is a mirror, and you're doing circle inversion.
Wait, what are the elements of the group?
The elements of the group are not elements of SL2Z, because each element. So inversion in this. What is inversion in the y-axis? It takes, so inversion, let's call it reflection across the y-axis. What does it do to a complex number z? If I have z, I need to take it to conjugation, real conjugation. So the way to do that is to negate and take the conjugate. So it's negative z bar. So it's an anti-homomorphism. It's an it's orientation reversing. It's not holomorphic. It's anti-holomorphic. And similarly, this, instead of z goes to negative 1 over z, it's z goes to negative 1 over z bar. And this is inversion across the line 1/2. Okay, so these are all orientation reversing. And so what you do, this is a standard thing to do with a billiard. If you want to play billiards, like let's say you want to shoot you have a ball, right? This is the first thing you learn in billiards. I have a cue ball. I have a ball here that I want to hit, and there's a ball in the way. So I'm going to try to bank it. How do I bank it? Instead of thinking about the billiard trajectory that gets me to my pocket, I invert across this mirror, and then I place this point here, and I place this hole there, and then I shoot a straight line. And because angle of incidence is equal to angle of reflection, that's exactly how I want to think about this. So when you have billiards, the double cover of a billiard trajectory will be a geodesic trajectory. Instead of
like double cover.
So instead of thinking of the single table, I want to think of 2 copies of the table.
So that's what the double cover.
Right. And now I go straight. As I move straight, that's the same thing as what will happen if I move by the billiard, bouncing off the wall. Okay. So as I come in here, the angle of incidence will be equal to the angle of reflection. So this angle needs to be equal to that angle if I'm moving this way, or either way, whichever way I'm going. Okay. So if we unfold that, when we unfold the double cover of this one tile into a pair of tiles, now instead of having, in other words, you take even words in the generators of these inversions, then everything's orientation preserving. And so as I come in here, the corresponding point will be here, and it will be the mirror of this. So if this was going to go like this and like this, then this is going to go like that, mirroring this.
Okay.
Does that make sense? Let me try to make a bigger picture.
You're saying the computation has to work out.
The computation has to work out. Yes. Let me make a bigger picture.
Okay, so I'm not if we hit that bottom part, but what if we hit like the left wall of our,
The left wall.
yeah.
So the left wall will
The
bounce
other-
off like
the
this.
other left wall.
The left wall. That one will bounce off like that,
Yeah.
with this angle being the same as this angle.
Oh, I see, and that's,
And that's exactly the same as if you just continue straight.
okay, that's fine.
So let me try to make this at more of an angle. So if this is my angle of incidence as I come in, then this would be my billiard angle of reflection. And now I just need to mirror that on the other side. So the point obviously mirrors, and now I'm going over here. Okay, so this angle theta needs to be this angle theta. So as I come in here, the trajectory goes boom and out like that.
That's consistent with.
And that's consistent with what I was trying to do here.
This is exactly what's happening in our case.
Yes.
Oh, okay, so that's just the thing, okay, yeah, okay.
Okay. And the way
That's
to
the same as the first proposal, I think.
did I get it wrong?
I don't know, I'm not sure, but this is actually clean. Okay, very
Yeah,
nice, very nice.
Yeah. So this is a better way to think about it. perhaps.
Yeah, I think this is what we saw and we were very scared because you go in like this and then
Yes.
you go the other way.
And then you come out, yeah, and then you
Yeah,
come
and
out and you're
you
heading
have-
that way.
Yeah, if you don't have that idea in your mind, I don't think it's very easy to see what's happening. with,
Yeah.
with-
Right, it's usually not difficult to prove once you know what you're looking for. Right.
Yeah, if you know what to look for, everything.
Yeah, yeah. And here's the equation. It's just how do you go from the equation to what's the reality?
Yeah, the motivation was legal because we want to make sure that if you hit the wall, you will actually go to a point that will go up. Because if you go to a point that will go down, it will not return. So that was why we were pursuing.
Yes.
But yeah, it's very.
Great. Okay. So this was the dynamics. So now we understand a little bit about this geodesic flow, which is the double cover of the billiard flow on a reflective manifold or bifold. So what is a closed? So here's a question. Can these geodesic trajectories, unlike upper half space, where once you start flowing, you're just moving as a straight beam of light, but now you have some walls to bounce off. Can a geodesic trajectory close up? Trajectory close.
This is incredible. This can even happen.
Well, I guess so. Well, I mean, it's not, here, if I hit the cue ball straight up, it's going to bounce off the wall and come back and do that.
Yeah, I guess like our generators are simple, and so you could think there's some symmetry there that could be exploited.
Right. Yeah, of course, there's a big difference between an interval rectangle as opposed to chaotic dynamics on here. So the geodesic flow will be ergodic. We haven't talked about what that means.
I mean, if you start somewhere in the imaginary axis and you go that way, just to the right.
Yes.
But that's not geodesic flow, right? Or do you mean just like?
The geodesic flow is going to go like this
Yeah.
and start doing some crazy stuff.
You can't go straight.
Okay. So can we make a very easy close to this?
There is one that is very easy to make. Okay, and it's the one where you have this, and if I look at the next fundamental domain, and I take this arc. So that is something that will go from here up. It'll jump to here. It'll hit this. It'll turn right around.
Right.
And come back there and go back and forth like that.
Okay.
So in fact, this is the golden mean geodesic. This is the gold. This is the smallest. Okay, now we're going to get into the Markov spectrum, and this is
I
the
guess
golden.
If you're saying golden mean, does that mean the visual point is the golden mean?
Yes,
Right.
this is the golden mean geodesic.
Concrete way to say
So
it.
yes, so that's where it came to close.
Yes, but let's see what. Yeah, so this will be phi and this will be phi bar.
I mean, the characterization is like nothing crazy, I guess. I guess my point was about like, yeah, why would you think about, it seems like if you start at some arbitrary geodesic, it seems like you should just go on forever.
And generically, it will. You can get any behavior you want. Okay, we're gonna talk about this. We're gonna talk about this. You can have scarring. You can have limits of closed geodesics converging on a fractal. Okay, so it doesn't have to have.
Limits as in where they hit to the right. What do you mean?
So, but let me. I will say as much of this as I can. So what does it mean for a geodesic trajectory to close? It means that if you start with this from this point of view, one of these cosets, you follow the geodesic flow at time L, and you hit exactly the same coset as you had before, right? What does this mean? G gamma, again, if G is some point and vector, so gamma G, this coset, is the set of all of these orbits, right? And wherever they are and whatever they look like all over the place. And then I flow by the geodesic flow by all of them. And it could be that after a while, this flow, whatever it does, there's something that comes right back to where it was.
Picture kind of stagnates.
The picture stagnates. So
Yeah.
did I not give a picture of it stagnating? I did not. Okay, I did not give it. Well, so this is an example of a closed geodesic, but okay. So the picture might stagnate. What does that mean? What does that really mean? How can we try to work out this equation?
No, when a gamma gets you from one side to the other.
Right. So if I start with just G, itself, and I flow by time AL, and I do this flow, I'll get to some point here, which was in the original coset. In other words, this has to equal gamma G for some gamma. So if this initial vector G, which corresponds to a point and a tangent vector, unit tangent vector, if G is a starting point of a closed geodesic, then there exists a positive real number L, and there exists a gamma in gamma, so that this equation holds. Okay, but this equation is very easy to solve. Let me multiply by gamma inverse on the right. So there's a matrix gamma in SL2Z, which I can diagonalize. Okay, so if this is so this matrix, now when is it diagonalizable? Over R.
Here you have the eigenvalues.
The eigenvalues are real and different.
Yeah, that's good enough.
So this implies that gamma has. Did we talk about the different types of motion? Hyperbolic, elliptic, and parabolic?
You didn't define them. I mean, the definitions are easy and they haven't been written down.
They haven't been written down.
You have the
Okay.
Hyperbolic.
Okay. Sorry.
Elliptic and.
So hold that thought for just a second. Classification of motions.
By traces, right?
Yes. Classification of hyperbolic motions. Okay, so if I have a G in G, there's three things that could happen. It could have two fixed points. G has two. So if I look at the equation G x equals x, what could happen? There could be, so this becomes a quadratic in x.
And G is SL2R?
Yes, yes, SL2R, ESL2R, whatever. Right? So if G is ABCD, this is saying AX plus B over CX. I'm so used to writing Z. CX plus D is equal to X. In other words, what is this? CX squared plus DX minus AX minus B is equal to 0. That's all. So that's what I mean. It's a quadratic. We can solve this quadratic. X is equal to whatever, A minus D plus or minus. Let's take one of them. Well,
your upper half plane in this case, so that dictates.
I don't know. At the moment, I'm just saying, what are the fixed points of this action? So here I get D minus A squared. Okay, let me write it in. D minus A squared minus 4 negative BC. So plus 4 BC all over 2C. And if you replace BC by 1 minus AD, AD minus BC is 1, then this comes out to, should we do the calculation, or you'll do it yourself? Yeah. So I'll write this as negative dA instead of A minus D, and then plus or minus square root of trace squared minus 4. So the minus 4 is that BC turns into AD minus 1. And the minus 1 is the minus 4. And then 4AD, there's a D squared minus 2AD plus A squared. And there's a plus 4AD. So that turns into A plus D squared over 4 all over 2C. This will be relevant in a second.
Yeah.
So if you have two distinct real eigenvalues if G has two distinct real eigenvalues, that will happen if T squared is greater than 4. This is if and only if the trace of G is greater than 2. And that will happen if and only if G has two distinct fixed points that are real. Two distinct real fixed points. I lost you.
Yeah, missing something, but if you have I can understand if G has two distinct real fixed points, we can go and say trace is greater than 2.
Yes.
But why eigenvalue? We didn't write Gx equal to lambda.
Okay. So okay. So you can also work out. There's a very. So this was a computation about fixed points. You can also work out what the eigenvalues of G are. And it'll be, okay, so a similar computation, maybe I'll leave this as an exercise.
You write it down on the paper.
Yes, okay. Exercise, work out what the, take G minus lambda I and determine it equals 0. Determine it equals 0, what is lambda? And it'll be something close, it's not exactly the same thing, but it also has T squared minus 4 in it.
Yeah.
For the same reason. Okay. So either G has two distinct real eigenvalues, if and only if trace of G is greater than 2, so trace squared is greater than 4, and if and only if G has two distinct real fixed points.
So what do we call these?
These are called hyperbolic.
Hyperbolic.
Hyperbolic matrices, hyperbolic transformations. So as a transformation, as an action, it's a hyperbolic transformation. As a matrix, it's a hyperbolic matrix, hyperbolic element of the group. Or trace squared is equal to 4, or trace is equal to plus or minus 2.
Double real root.
Yes, G has a double real root. And has one real fixed point. G has one real fixed point. And these are the parabolic transformations. Or the trace in absolute value is less than 2. And this is elliptic.
Complex.
Right, it has one fixed point in the upper half plane.
And one in the lower.
And one in the lower, yeah. G has one fixed point in the upper half plane. Okay, so the three transformations, if you want to see how they actually act, so the hyperbolic one has two fixed points. There's an X and an X bar that are the two fixed points. And G will be motion along this geodesic connecting these. Okay, so if you have something, if you have some blob here, then G will move it some distance. The distance will be the eigenvalue, will be related to the eigenvalue. G moves this along this blob to some blob like that. Okay.
Then,
This is hyperbolic.
right. So I guess what's always confused me about this is not so much the computations and everything, that works. But why do we give these the names hyperbolic, parabolic, elliptic? How do they relate to the conic sections themselves?
It's that the elliptic. So an elliptic. Let me finish this computation, and I'll be able to point to the three pictures. Parabolic has one real root. So that's, if you can think of that as the limit as x and x prime come together.
Right.
And so that has the effect of, so parabolic, I have a single fixed point, and I move along a horocycle centered at this point. So, so something here will move, if this is G, will move to something here. So the simplest instance of that, you can think about translation. If this point is at infinity, so another example, yeah, let's send one of the points to infinity. That's always a good thing to do. So another example is just, here's my blob, and G translates it over. Okay, so that's 1x01. This is the typical element is 1x01, which only has one eigenvalue. It's already in Jordan form. Nick?
Okay, so in the hyperbolic case, it's, the circle is, perpendicular x and.
Yes.
Two roots. Why don't we get a horocycle? Now it's like parallel.
So when the 2 points come together, the geodesic collapses. The geodesic gets smaller and smaller and collapses. So there's a completely different behavior that occurs
Okay.
in that limit. Let me put x bar at 0, and let me put x at infinity. And then all G does is scales. So if I have a little happy face here, then that happy face turns into a slightly skewed happy face.
Then, okay,
And the typical element will be, e to the t over 2, e to the minus t over 2.
with this picture in mind, I don't think I got what you were saying for the hyperbolic one. So you had a happy face on the left side of the hyperbolic one?
Yes. So this is just motion like this.
Yeah, that's it.
And if you think about what this is in the disk model, let's look at the same thing in the disk model. So in the disk model, if I'm moving from this region to this region, that's the same as moving from this region to this region. So here's the point at infinity, right? Using the standard Cayley map. So let's say this is 0. Okay, so let me draw this picture a little bit better. If this is 0 and this is 1 and that's -1. So 0 is here, -1 is here, and 1 is here. This is 0, -1, 1. Okay, so if I'm to draw a little happy face here, then translation corresponds to motion along the horocycle centered at infinity, so that this thing just slides over to this thing. Okay, but it's translation along all the horocycles. I mean, there's no preferred height, so there's no preferred horocycle. It's translation along all the horocycles centered at infinity.
And for the hyperbolic one, you were saying, the top picture?
This picture?
Yeah.
So this picture is translation along. So it's how should I put this? If you think about this picture, then I'm just multiplying by e to the t. I'm just multiplying everybody by e to the t radially. Right? That's what this takes any z and sends it to e to the tz.
Okay.
Which is just a radial rescaling. So what that does is the angles stay the same. So this moves objects along rays like this. So whatever ray you were on, if you were on this ray, then you move along to this, along this point.
That's what you mean by like, how
does it move?
How does it move?
Yeah, how does it move things?
Whereas you're saying the bottom picture, you're saying instead of more scaling.
Right.
So I don't have to draw my semicircle perpendicular.
That's right. That's right. So this is just there's a geodesic connecting these two. The geodesic is this ray. That's the only one that's a geodesic, but there are non-geodesics.
Okay, and then all of those are arcs of circles.
And all of those are arcs of circles, but they don't meet the boundary. They meet the boundary at whatever angle this is.
Please specify key points.
That's when
Yeah,
it
so-
collapses into a
So that's another way of seeing that when x and x prime collapse together, it turns into a horocycle instead of a geodesic. Okay, so this is let's get these. Well, they already are called something. So this is hyperbolic. Oops.
And the bottom one's parabolic.
This is parabolic, right? So this is para. Giper. Apollonius gave these names, by the way. This is para. This is, I already said, hyper. And then elliptic, what does elliptic do? So I have one fixed point in the upper half plane, and it just rotates along circles in that upper half plane. Some distance, not the full 360.
So you're saying if you have some blob, and you wanted to see how it maps into
Yes.
another blob.
Yes, so if I had a blob here, it would rotate to, I mean, it's not touching the boundary.
Yeah, so the circles are not centered at that point.
That's right, they're not Euclidean centered.
Hyperbolically centered.
They're hyperbolically centered at that point,
Right.
and it just gets skewed.
Okay, and then you just
Okay.
like, you look at your two fundamental domains or representatives, and then you do this, so you view that as your center and hyperbolic
Yes,
distance, and then you sort of rotate things around.
exactly,
Okay.
exactly. So this is elliptic. So now let me answer your question about why this it was given the same names as the conic sections.
Right,
So if you have a cone that's been cut by a plane at less than the angle of the cone, then you get an ellipse,
right.
which is a compact transformation. So after some finite time, you come back to where you started. Okay, so that's the elliptic transformation here. If you cut it exactly the same angle, then you get a parabolic transformation, same angle as the cone.
Yeah.
So you're parallel to the cone. That's where para comes from. Parallel to the cone is the parabolic.
Okay.
And then a parabolic transformation is like y equals x squared. It's growing, it's parametrized polynomially. Okay, and these elements, as I multiply more and more, if I take one parabolic transformation, I multiply it by itself more and more. These parabolic transformations in general, the unipotent transformation, grow polynomially. Because if I take powers of this, well, in the case of 1x01, it's just 1kx01. So here it's a linear polynomial, but in higher rank and other kinds of groups, it'll be some polynomials.
So it's kind of so that's the trace has to be one of these two specific values. The angle has to be this specific value.
Exactly. Now, if you go at more than the angle of the cone, you get your hyperbola, which is blowing up exponentially, right? It's hyperbolic sines and cosines that are parametrizing x squared minus y squared equals 1. If I take powers of this element, those are exponentially farther from, those grow exponentially. So this is hyperbolic growth. This is parabolic growth. It's still growing, but it's growing in a more controlled way. And this is elliptic growth. It's not growing at all. It's just compact.
Oh, okay. So these names were given after the growth.
These names were given in relation to what happens for conic sections.
Oh, okay. So I see, yeah. You
And it's a
said
very close,
ellipse, you don't grow. Parabola, that's like, polynomial growth, and then hyperbolic
exponential growth.
growing exponentially.
Yep.
So kind of an odd connection to make, I guess, in a sense. So you're looking at a cone and then you're.
It's a very natural one. I mean, it's exactly what that geometry is dictating.
I guess, but they don't literally make like hyperbolas, parabolas, or ellipses.
No.
I guess it's just.
It's what the
talking about
motions, yeah,
Yeah.
it's what the motions
How
are.
motions behave.
Yeah.
Okay.
Okay, so the fact that this is diagonalizable with two real eigenvalues, because we've diagonalized it, right? If, in other words, if I put the g's and g inverse on the other side, now I have a diagonal matrix, which is e to the t over e to the l over 2, e to the minus l over 2, and those are distinct. L is bigger than 0, means that gamma was, it has two distinct real eigenvalues.
Yeah.
So it's hyperbolic.
Hyperbolic, yeah.
Hyperbolic. So any idea, I gave you this closed geodesic that I claimed was the golden mean closed geodesic. Any idea what element gamma that corresponds to? Can you give me a matrix in SL2Z?
Like 1, I don't know.
That's a good guess. That's a very good guess. That one has determinant -1. You have to square it. The trace is 3. 3 squared is 9. 3 squared minus 4 is 5. This is the thing that generates the Fibonacci's, or the even Fibonacci's. And so if you take this matrix and you work out its two fixed points by exactly this equation.
You get golden mean and 1 over the golden mean.
Yeah, exactly. Okay, so the two fixed points are the golden mean and 1 over the golden mean when you connect them. So yeah. So let's this sometimes gets a little confusing. There's the G, which is the starting point, which is a point and unit tangent vector. And then there's the matrix gamma. So the G is arbitrary.
Right.
I mean, it's not arbitrary. It has to be, the G is the set of eigenvalues of hyperbolic matrices, right? But with what normalization, that's up to you. Eigenvectors rather, sorry. The AL is the eigenvalue. Okay. And what's the trace? What is the length? Sorry, what's the length? What's the relationship between L and gamma? Well, the trace of gamma, trace is conjugation invariant. So this is the same as the trace of AL. But what's the trace of AL?
2 times like the hyperbolic cosine.
Exactly. So this is twice the hyperbolic cosine of L over 2. So the length is the trace of gamma, what? Trace of gamma divided by 2 times arc cosh times 2. Yes.
I would have expected the closed geodesics to come from elliptic L's because elliptic motions, you put a point in flow, it looks like it comes back to itself. It's moving in a circle.
So what elliptic elements are there in SL2Z?
So the elliptic ones, these were
And look at the motion. We're not saying we want fixed points under an elliptic motion. We want fixed points under a hyperbolic motion. We want fixed points under the geodesic flow, but the geodesic flow is a hyperbolic matrix. It's a hyperbolic transformation. So the elliptic points are exactly the corners. And there are elliptic transformations
map these to
that map that move these tiles around. But that's not geodesic flow, that's elliptic flow.
Elliptic elements have a one is
There's a ton of elliptic elements, but up to conjugation, there's only this elliptic point and that elliptic point.
there are 2.
There's
right?
2.
And they have different orders, right? One of them is order 2 and the other one's order 3.
Exactly.
So
There's S and whatever this is, TST inverse or something. Okay. All right. So we have talked about the existence of closed geodesics, the correspondence of the closed geodesics, and the lengths of the closed geodesics. Now, had you started, so this was one starting point. Had you started at a different starting point, if we had started at Xi G instead of G, where Xi is some element of gamma, we would still get a closed geodesic, right? So Xi G that AT would still be something, some matrix times Xi G. Well, what's the matrix? We can get rid of the Xi. We can put the gamma that we know is there and put a Xi on the front.
yeah.
Okay, so it's not that matrices in hyperbolic matrices in gamma give us closed geodesics, give us unique closed geodesics. It's the conjugacy classes. So closed geodesics on X, which was the unit tangent bundle of Y, which is G mod gamma, correspond to hyperbolic conjugacy classes, or conjugacy classes of hyperbolic matrices. And there's one more thing that I want to note or restrict to, is that if I have a closed geodesic, so now I'm going to draw a schematic picture. This is sort of the pi over 2, pi over 3 infinity schematic picture. If I have a closed geodesic, that's just some curve, closes up on itself, does whatever it does, and I follow it around twice, that's an imprimitive closed geodesic.
Right.
So primitive closed geodesics, ones that, in other words, if I square this picture, gamma squared is still G AL squared G inverse. So, so L should be the least L for which you get back to a coset representative.
I had a question about this. I always had a hard time figuring out, like, how do you find out whether a matrix is primitive?
Is primitive or not? Okay, so let me just finish writing the word primitive on the other side. Primitive classes of hyperbolic matrices. So I'll show you in a second. Okay, so primitive primitive closed geodesics correspond to primitive conjugacy classes. In other words, ones that aren't like the conjugacy class of gamma squared is an imprimitive conjugacy class. But here's gamma. Okay. How can you tell if it's primitive or not?
In the matrix.
In the matrix. I give you a matrix and I say, is it primitive or not?
Yeah.
So I give you well, if I work out what gamma, if I had worked out what gamma 1 squared was, and I just told, I mean, we can work it out in a second. Like, but how would you be able to tell? Right, what is this? 4 plus 1 is 5. In fact, this will be the next, we should know that what it is a priori because it's the next Fibonacci numbers.
I don't know whether that's
So-
like primitive or not.
So let me, if I had erased this, pretend you don't see this. I give you this matrix. Its trace is 7, so it's hyperbolic. So it's going to give us a closed geodesic, or its conjugacy class will give us a closed geodesic.
Right.
Is that primitive or not? So let me show you how you can tell. There's a couple of ways to tell, but let me show you my favorite way to tell.
This is really important for later on, the quadratic form stuff.
Yes,
The
yes.
correspondence.
That's right. That's right. Which is what I'm working up to. So here's the way to tell. The closed geodesic. So following the geodesic flow gives us a cutting sequence. Now, the wrong way to do it is to do it from this point of view, this standard fundamental domain. And as you follow the geodesic flow, you say, did I hit the wall where I have to use T inverse to move back into the fundamental domain? Or did I hit a wall where I have to use S? So this would be called the S wall. This would be called the T inverse wall. This would be called the T wall, right? Which element do I have to apply to get myself back into the fundamental domain? And then you could follow. So as you follow the geodesic flow, you have a list of symbols, T inverse, and then I come out here and then I have to hit S. So these are just symbols. These aren't, not doing anything. Then S comes out and over here, and I have to hit T inverse again, and maybe I have to hit T inverse several times, T inverse, T inverse, T inverse, T inverse, T inverse, so this is T inverse to the 5, and then maybe another S and so on. And then I close up, and then I come right back to where I started. So it's this sequence over and over again, okay? That's one way of getting us a cutting sequence. A better way of doing things, and this was discovered by Caroline Series. So Series,
That's a paper that you referenced. In,
one of my favorite papers, is that you shouldn't look in the standard fundamental domain. You should instead look at the Farey fractions and the Farey tessellation. So you look at the Farey tessellation. We've talked about Farey tessellation?
I don't think so.
Okay. Farey tessellation, something very simple. The Farey tessellation is the orbit under SL2Z of the geodesics from 0 to infinity. So you can translate them. So now I get 1 to infinity, 2 to infinity, 3 to infinity, and so on. I also, if I apply S, well, S interchanges 0 and infinity, so that doesn't do anything. But if I apply S to 1 to infinity, it sends 1 to -1 and infinity to 0. Okay, and then I can translate that. And then, so it has all, so the Farey tessellation looks like this. It has all these arcs.
Applying S's and
Just from SL2Z.
Yeah.
So I apply every element of SL2Z to 0 infinity.
so you're seeing where you end up in the real line.
Yes. So the fraction, let's see, P over Q and R over S is connected by an arc in the Farey fraction. So P over Q has an arc to R over S if and only if Lewis, do you know this?
Would it be that the cross ratio is 1 or something?
Yeah, exactly. If the determinant of PQRS is equal to 1. Okay, so let's make that a little exercise. Now, this is a very fun thing to play with. If you haven't played with this, just start asking any question you want, and there'll be something interesting. Farey. Let me
So that's the same as saying that those are like adjacent Farey fractions, right?
exactly adjacent Farey fractions. Yeah, there's all kinds of beautiful stuff that you can do with this. So what Series observed is that if you have a geodesic that crosses, let's say, the vertical line, so you have a geodesic that does this. So here's my geodesic trajectory. I start from the imaginary line going in this direction. And what I do is every time I pass through an ideal, all of these are ideal triangles, right? These are all triangles. This region that's being tiled, it's a hyperbolic triangle with all vertices at infinity. Okay, so this is so that means I always have on one side, if I look to my right, I'll see, in this case, 2 corners of the triangle. And if I look to my left, I'll see 1 corner. And so where I see 1 corner, I'll call that an L. Yeah, if you imagine being in the middle here, you're inside the triangle. The triangle is getting cut by this geodesic.
Yeah.
And then I look to see where do I have 1 on which side.
Well, as if you were walking.
As if I'm walking. Yeah, and I look, I see 2 cusps over here on my right. I see 1 cusp on my left. I'll call that an L.
Okay, so you look to where there's 1.
That's right. And then I look, and then here, what do I see here? Another L. What do I see here? An R, because there's 1 over here and there's 2 over there. So this would be an R, and so on. So I make this sequence L, L, R, and then L, 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 R, R, and so on.
You hit the visual point or whatever.
Well, it's just an infinite sequence. I mean, if this is a rational number, then the sequence ends because you fall into the pit, right? If I go to here, then there's nothing else to do. I hit 3 and that's it. Game over. But except if you don't go to a rational number, then the sequence goes on forever. Now, what happens if you have a closed geodesic? After a while, whatever the sequence is, it comes back to the same point as where it started. And so this sequence will become periodic. So when the geodesic cuts the H triangle, let me write this down. The geodesic at the inside a triangle, so inside each ideal triangle, inside each ideal triangle in the Farey tessellation, the geodesic cuts the triangle, and it has a direction, so you know which way you're headed. It's an oriented geodesic. It's not just a curve. It's a curve with a direction. The orientation is crucial for this. It's an oriented geodesic. You don't know which way you're going. If you're going the other way, you would call it an R.
Right.
So you're going this way, you'll call it an L. So inside each ideal triangle, the geodesic cuts the triangle. And let's say we look to which normal vector, which normal direction, I mean, it doesn't have to be normal, we look to which direction from the geodesic has, let's say, 1 cusp as opposed to 2.
What happens if you're close to the cusp?
If you hit the cusp, then you stop. You don't assign a number, and it's like what happens what do you do with a continued fraction when it stops? It stops.
Okay, and that first box is an L because we have the cusp at infinity up above.
Yes.
The cusp at 0 and 1 down below.
Perfect.
Okay, so that's So why is that third one R?
So let's think about when we're heading,
What's the triangle?
it's this triangle
That whole thing. and then
between 2, 3, and infinity.
I see, okay.
Walk into Geodesic.
Oh,
one on the
I
right.
see, you have two on, okay.
Yep.
Okay.
And so what do you do with this sequence? So here's a really fun exercise. So, okay. Oh gosh, I'm not gonna get to anything today. Exercise. Let me make some exercises. Exercise. If you have a closed geodesic, if gamma is a hyperbolic conjugacy class, is a primitive hyperbolic conjugacy class with corresponding closed geodesic.
Is it saying is just trace it out once?
So if you have a primitive conjugacy class, so let's say we have this gamma. Okay, we can diagonalize it. So gamma inverse is some AL. We know what the ALs are because they come from the eigenvalues of gamma. We know what the length is. The length we already said is determined by the trace, which also controls the eigenvalues. So the length is determined. That means that we can work out what these G and G inverses are. So that gives us now that we only know G and G inverse up to the things that commute with AL. In other words, there's a choice. There's infinitely many choices where to start your geodesic. Okay. So you can start your geodesic somewhere. So let's start the geodesic on I up. On the imaginary axis. I don't know where, and I don't know in which direction, but a closed geodesic has to cross the imaginary axis. So if you started at the imaginary axis, you follow it forward to the fixed point. Remember, this gamma has two fixed points, x and x bar. Well, then you get this cutting sequence of L's and R's. So you get this cutting sequence of L's. So you get a bunch of L's and then a bunch of R's and L's and R's. And you group the L's, you see how many L's you have, and you group the R's and you see how many R's you have. And you group the L's and the R's and so on. And eventually it's going to, if it's a closed geodesic, then eventually it's going to, well, there's an even more general fact, which is even if it's not a closed geodesic, the continued fraction expansion of this number x is exactly this sequence of numbers. So even if you don't have a closed
In the
geodesic,
previous setting, what you do is you'd ignore the S's, right? And then your digits are just given by counting. the
That's
T's
right.
and T's inverse,
That's right. That's right. So you could count the T's and the T inverses, and it's almost always does what it's supposed to, but not exactly always. You have to like make little minor adjustments here and there. And this is the way that it always
works.
Yeah. So x will be the continued fraction 3, 2, 2, 1, 2, and so on. Whatever the sequences of L's and R's is, x will be the real number, which is that continued fraction. And so if this is periodic, then the sequences of L's and R's are periodic, because eventually you get back to the equivalent point down here. And so whatever this trajectory was, whatever sequences of L's and R's was here, that'll continue forever. And so if it's a closed geodesic, then x it will eventually periodize.
Yeah.
So now I have 2, 1, 2, 2, 1, 2, 2, 1, 2 forever. And so now let me ask you, how do you tell if a hyperbolic conjugacy class is primitive? How could you tell that this 5 is imprimitive? This 5, 3, 3, 2. So exercise. Y is 5, 3, 3, 2, not a primitive matrix. So if you work out what its fixed point is,
Right.
it will be and how do you go backwards from? You can go backwards from the this quadratic irrational to the matrix that gave it. right? If you have a matrix gamma, so that gamma x is x, well, you can work out what that is. It's exactly this matrix 2, 1, 1, 0, 1, 1, 1, 0, 2, 1, 1, 0. It's that this matrix will add 2, 1, 2 to the front of x. But if x had this periodicity, okay, you want to kill off the pre-periodic part by an element of SL2Z, and then you have this periodic part. So all you care about is the periodic part. And this matrix will add 2, 1, 2 to the front of your continued fraction. And if that gives you the same x back, that means your x was 2, 1, 2, 2, 1, 2, 2, 1, 2 forever.
Yeah.
Okay. So
what are you going to say here? That it's when it's purely periodic?
So when you find the number here, what does it mean that you've done it, that you've moved along this geodesic twice? What we'll find is if you moved it along the geodesic not once, but twice, it's the same number. This has the same, the fixed point of this, the fixed point of this matrix, let's call it M,
It has to be the same.
is the same as the fixed point of, well, M is gamma squared, in this case we know, but it's the fixed point of gamma has the same fixed point. But from the continued fraction expansion, we can work out what gamma should be. So this is a way to take square roots of matrices.
Okay.
Okay? What this really says is this sequence will be 2, 1, 2, 2, 1, 2 repeated. But you will recognize that that's the same as just repeating 2, 1, 2.
Yeah.
But from 2, 1, 2, you can get to the matrix 2, 1, 1, 1 by doing this with it. So that's your square root.
Wait, and how are you getting from the matrix to the sequence again?
So the matrix has fixed points. The fixed points we solve
Yeah.
exactly by this
It's just a
process.
limit, right? You just take the limit.
Not even a limit. The fixed point is this. You could also take the limit. You could also take, so there's
Just the matrix.
there's the matrix, there's its fixed points, and then there's the limit of the geodesic flow.
Mhm.
Right. Another way of seeing what the endpoint, but that's we're confusing the hyperbolic conjugacy class. So there's in this equation,
Oh, yeah.
GAL is equal to gamma G. We're confusing gamma with G. If I give you a G, then I can tell what its forward point is by taking the limit as L goes to infinity.
Yeah, but if you even go to a different like equivalence class, that might even end up giving a different visual point altogether. Right?
Yes, but the difference will be just some finite number of digits in front. The periodic part up to a circular translation will be the same.
Okay.
Okay. So this is how you can take square roots of matrices. I give you some big matrix, and I say, is this the 10th power of something or the 15th power or whatever? Well, if it is, then when you work out its continued fraction, when you work out the continued fraction expansion of the fixed point of this matrix, it will have a much shorter period than the period seems to be.
Okay, so this is a technique to doing that. You compute this continued fraction expansion. If there is some sort of duplicate in there 2, 3 times, and that tells you what sort of nth root you have to take in order to get back to.
And it tells you how to get the matrix.
Yeah.
Because from a continued fraction, you can write down this matrix.
In general, is there like an algorithm to take a matrix and write it as the product of the 2, 1, 1, 0, 1, 1, 0? Is this that algorithm, or is there another algorithm?
So this is one algorithm. Another algorithm, just to drive it in another direction. Another algorithm is to take some random point, Z, move it by M, and then put this point back into the fundamental domain, which you will do by T's by, T inverses or whatever, and then S's, and then T's and S's and so on. And then you put the point back in the fundamental domain. You've just written M as a word in T's and S's. Which is the same, yeah, it's exactly the same thing as working out the conjugate fraction expansion. It's exactly the same process.
Literally, because the S's is like you're doing the inverse.
The S is the inverse. Yeah, it's slightly, the S, there's a very slight annoying thing, which is that translation works the same, but S is -1.
Even one.
Exactly. S is -1, 1, 1, 0. In order to not flip upper half plane to lower half plane, it has determinant 1. Whereas these things all have determinant -1. So what sometimes happens, in fact, I wrote an odd length X here. You would not get, if you did this with a matrix, you'd get a matrix which is in GL2Z, but not SL2Z. And that one you would have to square to get something in SL2Z that has the same period.
So when you're saying primitive with respect to SL2?
SL2, not GL2.
And the same thing goes through with the same algorithm and
Yeah.
everything, just,
Yeah, in exactly the same way.
and so you're saying for general, if I give you a general problem, here's a matrix M, see that it's an integer power of like.
Yes, work out what it's
of
an integer power.
matrix.
Yep.
Then you just do this.
Yep.
Well,
So let me give you, there's a whole slew of exercises here that are related to this kind of question. So here I didn't go into the Farey. It was going to take too long to go into the Farey direction. So this was just a discussion. I'll put a link to this paper.
The problem was when I was looking up stuff like primitive matrices, primitive is a terrible adjective for any math thing, and so a bunch of other like unrelated things came up.
Yes. Right. Yeah, anyway. Okay, so we're almost out of time. Let me do one last thing. Do I have time for one last thing? I think I have time for one last thing. Which is, no, it's going to take too long. I want to connect to the next thing that we're going to do. I'll just say it in words. The next thing that we're going to do is we're going to connect this whole story of closed geodesics and primitive closed geodesics and their conjugacy classes and hyperbolic elements of SL2Z and their conjugacy classes to all the way back to quadratic forms.
Right.
Because quadratic forms also have roots. Isn't there some relation between the two roots of a positive discriminant quadratic form and some roots of a hyperbolic matrix?
Definitely takes more than 1 minute.
It'll take more than 1 minute to do it properly. So that'll get us a connection between these closed geodesics and binary quadratic forms, which will allow us to, which will be the starting point of finishing the Gauss finiteness of the class number.
Yeah. Which then, on the other hand, helps with Dirichlet's theorem.
Yes, and then I can at least tell you I won't prove Duke's theorem. To prove Duke's theorem takes a lot more work. I'll state Duke's theorem and I'll explain how that led to the ELMB question, and then we'll talk about how to make progress on that problem. Solve it.